Hi, I'm Tom and I talk about code. Welcome to another PlayStation 2 game hacking live stream. Today we're going to do more work on my Kingdom Hearts PlayStation 2 randomizer. The best way to probably demonstrate this is just show what's working already and what I've done. We did a lot of things in the last few streams. Some of them worked, some of them didn't, and we're moving forward towards, I think, a very cool place. So the idea is randomize all the chests and all the rewards in Kingdom Hearts for the PlayStation 2. I've already got something that kind of works, which is fun. I'll show that in a sec. Today we're going to fix dog rewards and chests being weird. We're going to try and shuffle chests, because right now I'm in this stage of I randomized every chest in the game, and that was doable. But I want there to be some kind of logic. So what I've actually done instead is repopulate the entire loot table for the game, and then I'm going to swap within that. And I can add more logic as we go, but for now, repopulating the table and swapping only valid entries is going to be my strategy. And then if I get that done, I want to find a better source of RNG. By better, I mean any, because right now we have no RNG. So let's have a look at what this currently looks like. It's written in assembly. This all gets loaded into... Well, we can get rid of these, actually, that's not there anymore. This all gets loaded into 4 kilobytes of unused BIOS space, which is really, really fun. It's fun reclaiming part of the BIOS. I've hacked the PlayStation 2 ELF loader to drop this in, and we've got a bit of logic that does stuff. So, for example, this is kind of like the main randomizer loop. We generate a random number by calling a function called EXOR shift, which is a pseudo-random number generator algorithm. That puts a random number in the register T9. We end that with hex ff to get a 1-byte value. We shift it left by 4 because an item index in the chest reward table is a byte. To grant an item at 0 in the lowest nibble, followed by, in the next 2 nibbles, a byte, which is an item index. So we encode that, and we get the next valid chest, and then we store it into that. We get the memory address corresponding to it. Whatever, it's great. We have this function called next chest index. I wrote that last stream. It uses this horrible bitmap to find the next valid chest. Last stream I ended on a bit of a weird note where my code was not generating correctly. And let me demonstrate this really quickly. If I get rid of part of this command in a very mysterious way, and then I make... So you know, this code, we add, we load a number, we subtract, we do this division, then we load the quotient, we do some stuff, then we load the remainder, and we do some stuff, blah, 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 blah. If we look at this code, what actually gets assembled here, objdump d, and this is a weird quirk of MIPS assembly that I was not really prepared for, objdump patch rando.o, you will notice that the code that gets generated is a little bit different. This break I didn't write. Load and branch, like this, I didn't write this. So what's going on? And this was a real head scratcher for a bit, because this break was just like hanging everything. It was a bit of an issue. And it turns out that when you divide in MIPS, it tries to be helpful and insert a divide by 0 handler. And we don't want that. And you told the compiler you don't want that by adding a fake register to operate on. And yeah, I don't know, it's weird. But also I think Zymus pointed out that I'm dividing by 32, so let's just not be silly, and instead of doing a division at all, we could just shift right by 5, right? 2, 4, 8, 16, 32. If we shift right by 5, that will give us, well, that'll give us the quotient, right? And then we want the remainder, but the remainder is just a logical AND. So we can do this. So we're going to shift right. T. What has my index? What has my value in it? What was I dividing? T0. Yes. Okay. So we're gonna shift right logical. We're gonna put it into T9, and we're gonna shift T2 by 32. By 5. We're going to shift by n for 2 to the n. Who have we got here? We have got Dinkelman. Welcome. Colt Black, whole radiation told you to open Twitch. Perfectly timed. You are just in time for the whole show. Whatever insanity is going to end up happening here. So this is good, right? This is good because this simplifies our code, and that's the kind of thing we want. So shift right by 5. And now we don't need this load like we had before. And similarly, to get the remainder in T8, what we actually want to do is just do a logical AND, right? We want to do an AND immediate. We'll put the result in T8. We're going to do T2. Where do we set T2? Hold on. I did this backwards, right? No? Knowing how old PlayStation 2's maths operations are, I wouldn't be surprised if you could divide by 2 without issues. Divide by 0 without issues. I think this is literally the case. I think you can literally... I think this is one of the things that they have to emulate in software if you want to do proper FPU emulation. Or at the very least, the divide by 0 behavior is different. Because at the end of the day, I don't think it's actually a hardware fault. Hold on, we can check. I can actually fact check myself for once. Divide. Positive, negative, remainder, signs, 0. Overflow, remainder, blah, blah, blah. If overflows divide by 0 must be detected, add an instruction that detects them. Divide instruction is asynchronous. The divide operation and check can be executed in parallel. If overflow or divide by 0 is detected, signal the problem to the system software. Then, if overflow or divide by 0 is detected, then to signal the problem to the system software is possible by generating. Interesting. Cool. That was fun. That was a good bit of poorly translated Japanese for anyone who has never read a Sony hardware manual before. Okay. So I got a bit lost about what these registers are actually doing. Hold on. So this is interesting because this state T0. Oh no, that's fine. Okay, so we want to replace this with, I'm going to put a hash here just so I can see, right? We're going to replace this. Try it and see if it catches fire, by the way. I will later, but I need to do this complete thing first, otherwise I'll lose track of what I'm doing. So this is our shift right logic. We're going to put it into T9. We're going to shift T0 right by 5 bits. That is equivalent to dividing by 32 because of how right shift and left shift work. So that's good. Now, instead of putting this in T8, we're going to AND an immediate with the result going into T8, and it's going to be T0, and we're going to AND it with 32, right? Because we just want the lower, so that's, yeah, 32. No, 32 minus 1, 31, which is this magic number, right? The lower 5 bits. So we want to just get the lower 5 bits. So that's good. Now we get rid of the divide, and when we make it and patch it, it's just going to work. It's just going to work. We're going to find out really soon if it works. Because if it breaks, it's going to break in an interesting way. Actually, it's probably not, because... Oh, we'll see. So if we can go... Oh, that's the wrong controller. I worked out why my controller wasn't working as well. This was really random. But it turns out that my controller was pairing with my PlayStation 3. And if it does that, so it'll like turn the PS3 on, and then it won't connect to my computer anymore, which is fun. And then my PlayStation 3's on, and I go out into the room later, and I'm like, why do I hear a fan? Why is there a very loud fan, the computer fan making noise? It's because my PlayStation 3's on, unexpectedly. Okay. And I'm going to find a solution to not having to do this fight every time I want to open this chest, because I feel like that was probably like half of the stream yesterday. But with that said, I feel like I'm getting better intuition for how to do this fight faster, which is good. Because I'm going to be doing it a lot to test this chest. Save states would be really useful. Okay, now actually, before I touch this chest, I'm going to make a save state so that we can play around with it. Save state. Save to slot 1. I could actually save and load from a file. That would probably fix it. Okay, so we get dogs. And we get these weird dogs, right? Where they're like dog 1, 1, and 1. which is not really ideal. So actually, let's have a look at what's going on here. Let's open up this debugger. Let's go to the chest table in memory. And the chest table is some combination of 1, 3, 1, 5, 5. It's 1, 3, and 5. And I think it's this combination, but that's actually apparently not right. 1, 3, 5, 0, 3, 1. Okay, I'm going to check. Hold on. This is silly. It's 351530. God, that's a really hard number to remember. It's a really tricky number to remember. Okay, so what chest index is this? This is the other thing we found. Let's get it in this. We found that there was a nice table that someone had written, a very helpful table. And this is the 2nd district postcard, so it should be index 16 in this table, which is nice and easy. So that'll be here. Maybe it'll be somewhere around here, right? Because we also worked out that reward, the chest, the lower nibble will be 4, so there'll be like a 4 in this position, right? 4 D4 C4 B4 A4. Huh. This looks a bit funky. This actually looks very funky. This looks incorrect. Because these should be 16 bits, but it looks like I'm actually only writing a byte at a time. Huh. So actually I've got a hunch. I've got a hunch for what's happening. So we're storing where are we? In this loop, we store a half word. We store 16 bits, right? But we may not always actually store 16 bits. I think something funky's happened. Or rather, we might be storing 16 bits, but actually, what these addresses are, right? So, next chest index is the index into the chest table. So T9 is going to be an index into a table stored at, oh no, sorry, T0 is the index. T0 is the index. So T0 is going to be the index we're looking at. T1 is going to be the table pointer, right? We load it here, we never set it again. So we're adding, oh yeah, it's right here, So we're adding the index to the address at the start of the table, which is all well and good, except each entry is 2 bytes. So we need to multiply T0 by 2 somewhere in here. And we could do that. I guess we could go... Right? We could just add it to itself and store that in T9 and then just add T9 to this, and then we don't clobber another register. That would make sense. Annoyingly, we have to do this everywhere we use it, which isn't great, I'm not gonna lie. And then in this loop, we need to do the same thing as well, because we get the next chest index. We need to double it. And that, I mean, this is something. Now there's a really, really big inefficiency here. There's a couple of silly things that we're doing that we can factor out later. But now let's just see if this works and actually gives us sensible dogs. And also I'm gonna try saving a state to a file this time, because I should have done that last time. I had my chance. Okay, here we go. I'm just trying to think if there's any other chests near save points. There definitely are, but ones where I don't have to play a significant amount of the game to get there. But also early chests are good. Have I figured out all the data locations myself? No, I've cobbled together a bunch of different resources. It's not really so much a public document. The best resource I have is an old version of a kind of like a mod called Kingdom Hearts Critical Mix, and I've got the patch file for that runs, I think it only runs in emulator, Oh, how do you miss that? And that has so many memory addresses documented, so many weird, useful things. I'm about to go. So the real struggle in this game is like doing things without spawning more enemies, right? Is there someone else here? Where'd he go? Okay, I'm gonna try and despawn him and stay near the chest. Cool. Yeah, but so I have worked out a few addresses myself. The stuff around the main loop hooking I worked out. Oh, there we go. Dogs. Real dogs. That was good. That was a nice and high number of dogs. We'll try this chest as well, which means another fight. And I still forgot to make the save state before I open the chest, which is phenomenal. I'll do it before I do this chest. But yeah, so I'm standing on the shoulders of giants, but also I've worked out a bit of stuff myself. It's a healthy mix. It's always a healthy mix. The KHPC speedrun tools. Oops, I didn't mean to make that full screen. The repo on GitHub continues to be a really good resource. Sure, let's put it in this folder. Let's say, let's make this save. And let's see if this, whoa. Okay, they're different dogs, which is amazing. That's good news. What happens if I go see the dogs? Is this final mix? Yeah, I'm... Oh, is it a final mix? This is an English patch of Kingdom Hearts Final Mix. I would not play the non-final mix version at this point. It's hard to go back. It's really hard to go back. Cool. So that appears to just work, which is phenomenal. We've got stuff being randomized. So we're putting stuff in, we're populating, which is great. And the reason I've done it like this is there are some things that I need to be in valid places, and then everything else we can just put some random garbage. That's fun. We need more logic for this part, but that's fun. Yeah, did I say healthy mix? I'm sorry. I don't listen to half the stuff I say. It's a good joke. It's a quality bit. I just I would need to have more like self-reflection to pick up on it. There's one thing I want to fix before we do this, and then we're going to start with a swap algorithm. I was brainstorming in my Discord a bit how I was going to go about this. Currently, when we reach the end of the table, we jump to this out of table label, which is okay because we know, just because of how this goes right now, we know that when we run out of table, we're ready to be done. But what I actually want to do now is go through this twice. So it's no good to just jump there. Well, I mean, I guess I could, and I could write more code and reset it and go through and have, but then when we run out a second time, we're going to jump back to that first label, and then you get into weird stateful stuff. So instead of branching here, we're going to say less than or equal to. So maybe we'll branch greater than 0 to just next chest index return. So if we have a real value, we're going to make a label called next chest index return. And this is where, you know, if we're out of chest indices, or if we have a valid index, sorry, jump to the next place. Just return it out. We've got it in that register, that's fine. And we can do this instruction in a delay slot because we say that we've clobbered T9 and I think T8 and S6. Very, very important register, S6. Got to remember that one. Cool, so we're doing this now. So end of table, right? But what do we do if we don't have the end of the table? Wait, no, that doesn't work. That doesn't work. Hold on. We've got a valid index, but we need to do the bit stuff. So let's keep it like this. Let's keep what we have. Let's say we'll keep the label called out of table, and we're just going to do the stupid thing. What I would really love is to not have to do a silly thing after this and reuse these two instructions, but I think that's actually too hard to juggle right now. So we're just going to do the silly thing, right? And that silly thing is, if we're out of things, we're going to load into T0 just the number 0. That's it. That's all we're going to do. And then we're going to return that. Beautiful. So if we're out of stuff, T0 is maybe even -1. right? And then we can branch if less than 0. So we're not going to call this out of table anymore. We're going to call this, what's this called? Done populate new table. First pass done. Right, we're going to put a label here. It's going to be first pass done. And when we get the next chest index, before we do all this stuff, first we're going to say branch if less than 0 T0. So if T0 is -1, which is what we do in that special case where we're out of stuff, we're going to branch to first pass done. And we can continue to modify T9 because T9 is the most temporary of temporary registers. Why not do it up here? Because we know that this is only called n times where n is less than the number of indexes. And we're writing assembly, so we're going to make all kinds of assumptions to make our life easier and so that we have to write less code. It's general good practice with assembly. I think in assembly, yeah, you do have to kind of walk this healthy balance between being thorough, because there's so many ways things can go wrong, and just not overwhelming yourself with code. You have the ability to make things very, very simple, to not have big function call overhead. If you just want to write little functions that don't call other functions, that's phenomenal. That's phenomenal. Wow. That is a very loud bot in my chat. We're just going to get rid of them. Lovely, lovely. Cool. All right. Just had to ban a spammer. And another one. Incredible. And another one. What's going on? With assembly, the simpler it is, the better. It's easy to lose track of shit you're doing. Exactly. Yeah, like, it gets out of hand. And I love that you can have things like function calls where you just have a lot less overhead to understand what's going on. You don't have to follow a whole stack frame. Function calls, they're a function, but they're not, what you really think of as a function. Okay, so we've populated a new table. Now we need to do something very cool, right? Which is, we've got this table, and I'm going to draw a diagram of this because I think it's useful. Okay, so this is, let's say this is the chest table. We discovered last time that it's actually quite sparsely populated. So if the blue is all the space, let's say these red lines are valid indexes, right? And they're packed together, and then there's a large gap, and then they're packed together again. There's like a couple of empties. Like, well, let's say yellow. Let's say this is invalid, I guess. Like chests you can't reach in the game, and then these are good. All right. So you get these kind of patterns like this, right? It's kind of in alternating sections, and we've got a bit mask that tells us which indices in this table are good, red, and which ones are just chests that you can never reach and we should never care about. So now what I want to do, now that I've populated a new loot table, is swap elements in this list, right? But I only want to swap good indices. I don't want to swap a good index to an invalid index, because then I've taken an item that I want to be in the game and I've put it in a chest that you can't reach. Likewise, I don't want to put an invalid index in a good spot because I haven't put anything in them. Mostly they just have weird placeholder items like potions. And I don't want this many potions. That kind of potions. I don't want this many potions. That kind of sucks. So we have two things, right? We only want to go from good to good. How do we get an index that is only good? How do we make sure that we can get two indices from that only correspond to bits set in my bitmask? Which CPU was the PS2 based on? It wasn't PowerPC. It was not PowerPC, you're correct. It was based on MIPS 3. So this is a MIPS 3 CPU with some MIPS 4 stuff bolted on. It is a bit of a mishmash in an interesting way. Cool. So how do we generate two indices that are valid, a valid pair that we can swap? Here's my thought. Okay, let's say we generate an index, right? Let's pick a random number between 0 and the size of the table. So 1, x is in 0, 479, because that's the size of the table. And there's a decent chance that this points to an invalid index. I think there's more invalid chests than there are valid ones. Okay, so let's say we're pointing here. What do we do? What can we do with this to get to a valid index? Well, we could start adding 1, right? We could say +1 and +1 and +1 and +1 modulo table size. Eventually we'll roll around here, +1, +1, +1, and we will end up at a valid index. That's kind of cool, right? That means that we would always guarantee that we get a valid index. But there's a problem with this, especially because the table's quite sparse. We're going to massively bias towards the elements at the start of a group. We're always, much more often than not, we're going to end up at the first element of a group because all of these map to the first element, all of these map to the first, all of these map to 1, right? So that's not good. That's not very random. And we want to be as random as possible. So here's a thought, right? Add if... let's say while x is invalid, well, we have a way of checking if x is valid or not. If while x is invalid, x equals x plus, let's call it mu, because that's a cool Greek letter, mod 479. Now, if mu is 1, that's really boring and we get this bad distribution, but maybe we can find some value for mu that is gonna give us a much more random seeming walk. So the challenge now, I think, and because we only have 479 entries, perhaps we can actually do some simulation and find a much more balanced, a much more fair stride that will give us more balanced results. I think that's interesting. I think that would be kind of cool. So let's write some Python code, okay? Let's call it sim.py. And we're gonna have a list. We're gonna make, well, let's say table size 479. And let's say counts, right? We're gonna have an array of counts that are all initialized to 0, okay? Let's make a function called step. And step is going to do one simulation. So it's going to say index equals random.random, I guess, times table, random int. Can I do random int? I always forget in Python. Hold on. Is it randint or randomint? Randint. Yeah, cool. That's excellent. Thanks Python, randint, so between 0 and table size, randint a less than or equal to n less than or equal to b, so I want table size -1, and we'll say counts in index plus equals 1. Cool. Toss coin to decide what to implement. I mean, that's a random generation for like me as a human, but it doesn't really help. It doesn't really help the simulation. Man, I would love to have just like an array of coin flippers, right? Just like pay 10 people to sit there and flip coins all day and then sell randomness to the world. That would be cool. How many random simulations, how much meaningful randomness could you export to the world over an API if you had like 10 people flipping coins for 8 hours a day? Right? How valuable is that to the world? Does someone already do that? That's probably already a service. Someone probably already had this idea. So, oh wait, hold on. I forgot the important bit, which is while invalid index. There we go. That's what I meant. That's what I meant. I forgot the important bit. Sony's always returns random, returns 4. Is that, what system was that on? That's insane. It's not even a good approximation of pi. Like, what can you do with 4 as a random number? So invalid. So we're going to say bitmask equals, and we're going to copy and paste from that other file because that's kind of good. Rando.asm we're going to copy this magnificent bit mask that I built last time, which I actually generated with a Python script. So it's kind of funny. I've like copied it into an assembly file, and now I've copied it back. Let's actually just say def get bit. Cool. So we want to implement the algorithm we just had in assembly, but now we're going to do it in Python, and that's going to be easier, hopefully. Let's say word index is x divided by 32. And we'll say bit index is x mod 32. So this is which word in this list we're inside, and this is which bit inside that word we're inside. So that's good. Double slash divide means just do integer division, so we throw away any decimal part. Cool, that's excellent. So now we just say bit mask word index and one left shift bit index. If it's bit 0, it's just 1. If it's bit 2, we left shift by 1. So that's good. That's good. Return. This greater than 0, I guess. Right? So it's either true or false. Is bit set. While the bit is not set, we keep going. Cool. And now we want to run the simulation. Now I want to run the simulation. So let's say, and then how do you work out how random this was? Do I just print them out and eyeball it? I mean, that would work. Let's do that for now. But let's do this cleverly. So let's say for I in range table size, we'll print out counts I with a tab, because tabs are cool, and if I mod 10, if I is bigger than 0 and I mod 10 equals 0, so every 10 things we'll put in a nice little new line. Cool. And then what do we need? We just need to say def trial an interval. So n times we say step interval. And that's it, that's all we do. During the PS3 or PS4, it was on the PS3, they dumped private keys because of that. I know the infamous history of the PlayStation 3 key dumping. I've got a jailbroken PS3 because they can just sign their own updates. And also, long live chaos. Sorry, no, that was the wonderful scam account. I can't quite see the full name, but I think that was the amazing scam account. Wow. Followed. I'll take the follower, thanks. PlayStation, that's insane. The random number generator always returned 4. What a thing to leave on the table. Cool, so let's say trial interval. Let's do 100,000 loops, and let's test 1, and then let's print the table. When I started writing this, I didn't really think about how I was going to quantify. Oh. Is this not Python? Can I not say not? Do I have to say not like a grub, like someone with extra keys on their keyboard? 6. Yep, that's a stray line. A stray character. That makes sense. Random. I should seed the RNG as well. Okay, cool. This is real. So we can see there's quite a few things that never get hit, and that probably makes sense, right? That makes sense because they're invalid. So what we want to see, and actually this isn't too bad, but what about the difference between the best and the worst? What about the average? No, the what do I want? The average will always be the same, right? We want I guess the top n versus the bottom n. Let's do that. Let's quantify the results as top n I like that. I like that. I'm also I'm gonna move step inside here. Because I think that makes more sense too. That's good, and counts. And then we return count. Wait. Yeah, we return counts. Only at the end, only at the end. So after we've done this, we return counts. Cool. Index is this, blah, blah, blah. We get rid of this. Instead of n, we just say interval. Okay, cool, cool, cool. Now print results, we're just gonna pass for a second. Trial interval, 0 position arguments, 1 was given. Trial interval. Yep, that is all good. Oops. Print table takes 0 positional arguments. Ah yes, that also makes sense. Counts. Wellinator, hello. I know that name. You're in the PS2 Discords, right? Welcome, welcome. Good to see PS2 fans here. We're doing some weird PS2 stuff today. This is fun. This is fun. So yeah, I think I want to take the difference between the most and the least counted elements, right? So I want to sort it, and I want to take that difference. So let's say sort. Do I do counts.sorted? I think this modifies in place. Wellinator, but yeah, Wellinator, how are you going? Are you working on any PlayStation 2 stuff at the moment? Is there anything cool going on in your world? Counts.sorted. So we've sorted the things. We want to say counts. We want to look at the range of these things. Let's say print results. And yes, I do mean, oh, it's sorted. Yeah, so I want counts.sort. And that was sorted backwards, but that's okay. So one of these things got 12,000 hits and, oh, actually, but I want to filter out the zeros. But do I want to filter out the zeros? I want only things that are valid in this bit mask. Oh no. Okay, we're gonna do this. We're gonna do this. We're just gonna push. We're gonna say for I in range table size. But yeah, Wellinator, if you're confused why we're writing Python right now, I'm doing some simulation because I'm trying to do a random walk over a sparse table as part of my Kingdom Hearts randomizer, which is quite the endeavor. Quite the endeavor. So for each thing, if is bit set I, we want to valid counts. We want to append this to valid counts. I counts I. Cool. Now we want to get valid counts sorted. And we expect to see something similar, but the bottom result should no longer be 0, and now it isn't. That's good. That's good. Learning some V stuff to implement fog. That is really cool. I would love to do some fogging. Moody, low draw distance stuff is well suited to PlayStation 2 homebrew. I would love it. So now instead of this, we're going to return this as a metric. We're going to say valid counts -1 minus valid counts 0, right? So now we've got this we'll call it quantify, right? Because this is like, how good was this thing? So let's try a couple of different numbers. For I in range, let's try the first 1,000 numbers and see if we get anything good. So we test 10,000 times, see what this is, and we're gonna say results. I will say results, append, quantify res. And actually, we probably want to put it with the number that it came with. And then let's just print results. And just see what it looks like. This is going to take a second. This is going to take a bit more than a second. My CPU fan is spinning. It's a pretty tight loop. I wouldn't have thought it would take this long. Like, Python's slow, but it's not that slow. Am I doing something silly? I mean, I guess it's like 1,000 times. Should I cancel this? I don't know how long this is going to take. Maybe I should have started with a smaller number. Okay, I'm going to control C. Let's just go down to 10. Let's see in the first 10 numbers what this looks like. Okay, hold on. Whoa, whoa, whoa. Let's lower this number too. And it's still taking a while. That's weird. That's weird. Because, like... Hold on. Hold on, I've got to be doing something wrong here, right? Also, I'm printing results every time, so... Trial interval... It's never finishing? Huh? Oh, wait, hold on. There's a really good bug here, okay? Think about it. Why was nothing ever getting printed? Because I'm doing I in range, right? So let's go back to 10. Let's do the first 1,000 numbers. Let's go back to 100,000. What's the first interval I'm trying? I'm trying 0, right? What happens in 0? Index plus equals 0, so that's not good. Cool. So we're gonna index plus 1. Now index is out of range because when I plus equals interval, it needs to be index plus interval modulo table size. Cool. Okay, there we go. Now this is gonna actually work. Hold on, I'm still gonna start with a lower number because I'm nervous. 10. 10 is good. It's a nice small number. There we go. So in the first 10 integers, we can see like 1 is really, really bad. 2 is a little better. Let's fix this so that it's actually I plus 1 because that's what we're really testing. So the bigger this number is, the bigger the difference between the most visited element and the least visited element. And we want this to be as close to 0 as possible. We want to minimize this value. So, 6 is looking pretty good. 7 is looking really good. 8, for some reason, has done really well. And these appear to be relatively stable. It appears the fact that these numbers are the same between trials gives me confidence that 100,000 is a good simulation amount. That would be good. Cool. So let's try upping this number. Let's try the first 100 numbers. And after this, I'm going to need to actually write code to pick out the best candidates from this, right? To find the ones that do minimize. I'm going to have to write some kind of comparison, right? Cool. So what looks small? What's the smallest number in here? It would be really good to get this as close to 0 as possible, right? Maybe that's not possible. Maybe over a table of size 400, that just is not possible. But for one thing, we can't increment this by the table size. So what if we just do table size -1? And this is actually big enough that we can eyeball it, right? Small enough we can eyeball it. 1,000 was a really silly number because we were going to hit an infinite loop when we hit the table size again, because anything that missed the bit set flag would get stuck in an infinite loop. I'm just going to check my phone while this spins. Cool. So it looks like we might struggle to find a really good value here, which is a little bit sad. But I guess... The more random it is, the less discrepancy there should be between these things. And it's okay if there's some discrepancy. 1,000 feels significant. Okay. This is maybe a few too many numbers to parse. Is this... Hold on, is it symmetric? This is symmetric. So we actually it's roughly symmetric. So for example, if I'm getting like motion sickness scrolling through this. So I look at 10, right? This should be the same as 400 and... So what number was this? 1,700. We would expect to see 1700 here as well. So it's symmetric. It's symmetric around the halfway point. So we can actually do the range like this. Now, we want to use sorted, and we want to use it with a key function. Key equals, yes, lambda. Okay, good. So let's say sorted results key equals lambda x x1, right? We're sorting by the actual value in the tuple, not the thing. So we're gonna print in this order. And actually, maybe we only want the top 10. Right, it's from 0 to 10. So let's do this. Float cannot be interpreted as an integer. That's because we just need to divide like this. So what's the top 10? What's the best performers? This still looks worse than I wanted it to be, which is a bit sad. We're spinning, the fans are going. I also wonder on average how many swaps you have to do to get anything good. So 131 has the best result here, but it's very similar to 142 and 18 and 112. Like, these are in a similar ballpark. So over 100,000 simulations, 1,000 of those are more biased towards the more biased towards the most visited element than the least visited. So 1%, I don't know, 1%'s maybe acceptable. That actually does feel quite random. And this is almost entirely stable, which is cool. So I think 131 wins. The conclusion is 131 wins. That's excellent. And let's make this a constant. Let's call it set random walk, random chest table, random stride. 131, a very important number. Okay. So we want to pick a random number. We want a loop to happen some number of times. So let's first off, into the register, let's use S6. No, we can't use S6. Let's use V0. Let's put the number 100 in V0. Let's say we're going to do 100 swaps. Let's say 200. Let's do 200. Let's start with 10. Let's start with 10 swaps. Let's start unambitious, okay? I think that's good. So the second pass, the first thing we want to do, so loop 10 times. We're going to loop 10 times. Each of those 10 times we're going to find two indices, and we're going to swap them. So we need to generate a random number, and we're going to put, that comes out in T9, so we're going to jal EXOR shift swap loop. We call this swap loop because this is the loop where we swap things. We're gonna, so EXOR shift puts a number in T9. I need to double check this, into T9. So this random number in T9, we're gonna straight away, we're gonna call EXOR shift again, and while that's calling in the delay slot, we're gonna add IU, we're gonna add it into T0. So we're still adding T9 to 0 and storing that in T0. We're moving T9 into T0. And once that's in T0, we can call next chest index, but we don't want to, well, let's do that. So we have a random number, except we want to do next chest index with a random walk. Let's copy and paste this function. And instead of out of table, okay, let's, I've got an idea. This in the chest table, destroys T9, T8, and S6. And instead of adding 1, we're gonna add, well, first off, we're not gonna do that straight up. We're gonna do that before before we branch, after we branch. That's kind of good, right? That's a good use of the delay slot. And we're gonna add chest table random stride. Chest table random stride. So we come in, we look for the next index. If we're outside the table, we need to make an adjustment. We need to make a little adjustment. That adjustment is going to actually be, instead of saying that we're done, we're going to loop back around. And we're going to loop back around by subtracting into T0 minus the size of the table. Does that work? Yeah, because it's bigger. So what we're saying is T0's bigger than T9. In that case, we want to adjust T9 by subtracting the size of the table from it, which is T0 by subtracting T9, which is the size of the table. And then we branch unconditionally back to next chest index with a NOP. And actually, we can put that in the delay slot, which is kind of cool. Okay, we're making better use of our delay slots. This is nice. And this should run the algorithm that I just wrote in Python, just in a kind of janky way. So next valid chest random. Let's say next valid chest random, even though you have to call the XOR shift yourself. Should I just, no, I can't call the XOR shift inside here. You can't call a function within my jank functions. That's not how this works. So we've got a random number. We get a second random number, and before we do that, we store the first random number in T0. Now we're going to do the same thing. We're going to say next chest, what did I call it? Next valid chest random. While I do that, I'm going to move this into, I guess, T2, this other thing. So T2, T9, 0. Because, again, I've said this a few times, in MIPS, after you jump to a function, there is a delay slot where something happens. Maybe a lower value. Yeah, okay. So when we get to this point, what do? We need to... So at this point, right here, T9 is valid chest index, T0 is, oh no, T0 is a valid chest index. So we want to add IU T0. We want to move T2 into T0, and then we want to call this again, next valid chest random. While this is happening, we probably want to do something else. So, what can we put in this delay? I'm honestly just going to put a NOP for now, and we'll probably be able to put whatever instruction comes next, but I just need to space out my delay slots nicely. Next valid chest random. Okay, so. Oh wait, hold on, I need to put this somewhere too. Let's add IU. Right, so after this we say T0 and T3 are both valid. T0 and T3 have our two valid indices. This is a lot of register shuffling. So now we need to swap them. So we need to get the address at T0, read the thing out of it. We can turn both T0 and T3 into addresses at this point. We can add IU. Let's say T0, T0, oh, except we need to double it. We need to add IU, T0, T0, T0. We need to double both of these registers. Right? Because currently they're indices, and we need to turn it into a 2-byte offset that we're going to add to a pointer. So we're adding T0 to T1, which is the address of the chest table. Then we can do the same thing here. So T0 and T3 are addresses of chest entries. So we're gonna load 2 bytes out of, we're gonna put it into T9, we're gonna load from T0. We're gonna store from, wait, no, we need to do this here as well. We're gonna load into T8, I guess. And then we're gonna store the word from T8 into T0, and we're gonna store the, half word from T9 into T3. And now they're swapped. Excellent, excellent. Then we're gonna just subtract 1 from V0 and do it again until it's less than 0. Cool, cool. So we're gonna load into, let's just dump it in T9, we'll put the number 1, and we subtract from V0 minus 1. Branch if greater than 0 to, if V0 is greater than 0, go back to swap loop and do it all again. Nop. Because there's got to be that nop to close us off. Okay, excellent. Now let's build this and run it, because there's nothing that can possibly go wrong. Make patch rando.bin. Okay, so there's a couple of problems. Out of table already defined. Must be, operator 3 must be an immediate expression. Oh yeah, yeah, that makes sense. That's really funny. Well, I could also just turn this into an add. I don't know, maybe add IU is actually better. What's this? Hold on, what line's this on? 99. Oh yeah, I've done it more. In this case, this does just need to be an add. Just too much muscle memory writing add IU. Okay, 85, that's good. 85, because I forgot a comma. And then what do we have? I tried to set unrecognized symbol. Out of table. I'm just gonna call this label wraparound because that's better. Undefined reference to chest table random stride. Chest table random stride. Huh. It's because I forgot a comma again. Oh my gosh. I have gotten so many bots today. Why am I being so spammed with bots? Ridiculous. Excellent. Let's fast. Let's make our patch and see what happens. Cool. Let's see what happens. And we've got some TLB misses. We have broken everything. Let's see what happens here. Let's see what's going on. So we're going to make a breakpoint. We're going to put it at our favorite address, ff000, which is where my code starts. Viewbot's been a big issue lately. No clue what's going on. Other streams you moderate get a few dozen a day as well. Wow, that's crazy. That's insane. You love TLB misses. Zymus, I am dividing by 32 with a right shift now. I hope you're proud of me. I fixed it. It's so much better. No more divide sealants. I love that we went down this division compiler issue rabbit hole and we were solving the wrong problem the whole time. Okay, so we're gonna have to step over some stuff here. I think I know where this is going wrong. I have a suspicion. So this is all fine. This is just setting some stuff up. This happens a couple of times. Okay, so add to not. What's v0 here? When do we set v0 to 10? When do we set v0 to 10? I'm just gonna watch for v0 to change. I think that's the best way to go here. V0. Oh yeah, this is going to go quite a few times. Hold on, this is a big old loop. So what's the branch? Yeah, we branch here. Okay, so let's go after this. This is the dog loop. 9C. Must be here, right? We must be around here somewhere. So what's here? What if I run to here? Star half word and shift left. Branch false. Ah, here we go. So it is this function. Okay. So it's this line. Hold on. Oh no. Nope, we didn't crash. We didn't crash. We were close to crashing, but I don't think we crashed. Okay. This is good news. This is good news. This is fine. This is fine. That's not fine. Hold on. Is it? It is. It is. T8, T0, SLV. So this is my function, right? This is one of my functions. And then this should be the other one. So let's see if we can jump to the start of this function. JL. Aren't I afraid a team of mercenaries funded by Sony, Disney, and Square Enix? Honestly, like, the mouse is probably the scariest part of that whole trio. But yeah, it's a risk. You know, there is a risk that they say stop doing this. But I'm also a small live streamer in Australia. I'm not I don't think that they will. And if they do, I'll have to stop, right? Because I'll respect what they say. But I don't think I've done anything particularly bad here, right? You're allowed to reverse engineer stuff. So yeah, I don't know. It's fine. I think this is the function call that's bad, right? Or is this the good one? This one works. Okay, so let's step out of this bad boy. So we don't care about this function, we care about the other function. We care about this one, right? So let's step into this. Here we go, here we go. And this is where, yeah, v0 has 10 in it. Okay. So we do the subtraction. This is true, apparently. Huh. T9. T9 is -1. We subtract. Wait, what's T0? T0 is... this number? So T0 is -1 to begin with. Oh, of course it is, right? Because it's just a random number. Hold on. I forgot the modulo part. I forgot the modulo part. the remainder, right? So hold on, I need my my shady doc back. Div. So which one is remainder is stored in high. So I want the remainder, right? If it's a random number and I divide it by the size of the table, the remainder is gonna just be some random number. Yes, yes, this is correct. It's not a power of 2, so I can't really do that. So I was very silly. I was very, very silly. Before I call this, I need to do something with this number. So we want to div, we want to li, let's put it in T9. No, that comes in T9. Let's put it in T8, I guess. We're gonna load the number 479. We're gonna divide T0 by T8, and we're gonna move oh, and I need to put an extra 0 here to stop it trying to insert extra instructions into my code. We're going to get the remainder, we're going to move it back into T0. Cool. Now when we call this function, in the delay slot, we're going to divide... we kind of need to do this as well. T0, T9, T9. In the delay slot, oh, I got rid of a, did I? No, I didn't. Okay, so in the delay slot here, we're gonna divide T9 by T8. Then when we come back from that, because we don't do any divides in this function, we can move the remainder into T2. So yeah, so this is good. This is good. I think this does everything I need. Let's find out. There's only one way to find out. But that makes sense, right? And this is actually kind of good. We can use the low and high registers. We can issue a divide when it should have probably the most minimal impact possible. There are a couple of TLB misses there. That makes me a bit scared. But let's press forward and see what happens. That would crash a real console. We have the benefit of the emulator being a little less sensitive, which is wonderful. Actually, hold on, I have a save state. I should have a save state. I saved a state. Did I not save a save state? I can't see it. Okay, well that's fun. I saved it, right? I definitely does it know that it's the wrong game ID? I don't know. Does it know it's the wrong game hash? Let's go open a chest and see what happens. This is the best way to find out. This is how we do it. So. Mistakes were made. He's going to the moon. Oh no, not the jump slash. Wouldn't loading a save state override my patch? Yes, that's actually a really good point. That would completely override memory. Also, we have that fun sound to deal with now. Do I have enough little bubbles here to... Oh, it goes away in the out of battle anyway. Okay. They're dogs. That makes me suspect that... Well, I guess I only did 10 swaps, right? How many TLB misses did I have? More than 10. Oh gosh, that was a lot more than I realized. Okay, maybe we need to look at what those are. Maybe that's gonna give us some hints. I mean, it didn't completely blow up, right? Which is good. But let's have a look at what's going on. That just makes good sense. All right, I wish I could make this bigger. I wish I could zoom in on this somehow. I always say it, right? FF000, did that not get hit? Oh, it's because it's the wrong type. Hold on. Let's restart you again. And now it's going to actually break when it executes the code, not when it tries to read or write the memory. Isn't that nice? So let's go. Let's look at my code. Here's the stuff, blah, 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 blah. This is my bit mask, which is very cool. This shift left, branch, add array, subtract branch. So this is it, right? This is the code. This is where we do it. Because we subtract, yes. Okay, so we're gonna run to here. This is good. So what happens? We do the subtraction. So what is T9? T9 says, what's T0? T0 is what we pass that argument in. 158. Very good number. Very, very good number. Sorry, hex 158. Not 158, but still a very good number. 344. Valid, good number. We do our subtraction. We don't branch because it's not because it's in range. We set T9 to 20 in that hex 20 in that delay slot, which is good. We shift T0 over to the right. Why did I put hex 20 here? Why 32? I probably don't need the constant 32 anymore, right? We put that in T9. Shift right. Now, T0 is 158. We shifted that to the right. Just give me SRL. Shift right logical. Setting zeros into the sign extended. Sign extended. Why is this getting sign extended? Is there a shift right arithmetic? Arithmetic does the thing duplicating the sign bit. Sign extending to 64 bits. Oh, that's gross. But I want logical, right? Like shift right logical is what makes sense here from 32. Okay, that's disgusting. Do I need to do a double shift right then? Is that gonna stop it? Is that gonna... Logical is what I want. Yeah, good. I know some things. Lower odds 32 bits. Inserting zeros into the emptied bits. Sign extended and stored. They're not signing. Like sign extend would, yeah, an arithmetic with sign extend below 32-bit. That makes sense. So do I want SRLD? Right, will that, or SRL? What does this say? By the bit count, it's supposed to say. This does no sign extensions. Let me try this. This might be the wrong solution, but it might also work as well. You don't think so? What? So why does sign extension trigger here? Hold on. Like I get the idea, I get what's going on, but I don't understand why sign extension is being triggered. Because we have, in this case it was hex 158, right? So we had, which is the bit pattern 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0. We right shift by 5, which means that we're chopping off this. So we expect to get 0, 1, 0, 1, 0, 0, 0, or hex. What's this? 8. This is A. All the 32-bit instructions will sign extend to, but there's no, this shouldn't sign extend, right? There's no sign to extend. We were just getting a very negative number. Like this feels fairly clear cut. This doesn't seem like there's much room for ambiguity around how this works. Let me see if I can step through that again. Yeah, it means it's, but it wasn't in this case, right? That's what is funny here. So, okay, so maybe that was a red herring. Maybe that's actually not the problem. Where do we get some funky instructions? That's what I look for. Then I scroll up. Then this is the thing. So this is the function start. So let's find, so shift right. Okay. So T0 is 158 and we're shifting right by 5. And what goes into T9 is A. Wait, that was right. Okay, maybe I'm misreading. Maybe I read the wrong thing. It's really easy to read the wrong row along here. So that's good. That was a dead end. We load 10. We subtract the size of the table. T8. So T8. Oh, 16, sorry. 16 minus, so where T8 FF2, what do we do with T8? FF254. We add that to T9, then we load whatever's here, which looks like real data. Oh yeah, that's, sorry, that of course, FF254, FF254, that's my bit mask. Beautiful. And then we AND it with so we get the remainder. We set S6 to 1. We build a mask in S6. We AND it together with T9. T9 is going to have the result, which is bigger than 0, so this is a valid index. Yeah, so that's good, so we jump out. Nice. We jump back in. The T0 is a very big number. Okay, well that's a problem. That is a little bit of an issue. Let's step out of this bad boy. That'll have a TLB miss. How did that happen? How did that happen? Okay, so this is where we want our breakpoint, really. This is where stuff really gets a bit off the hook. So high and low. This is fine. We're gonna run. So high and low. Why is high? Why is low? The remainder. I guess I just want to do the same thing in a sense, right? I guess I would have thought the remainder of dividing by 479 was a number in the range of high. Yeah, I would have thought that this would always give me something in the range 0 and 479. Why was that? Why were they such strange numbers? Wasn't really prepared for that. Okay, well, I guess the question is what actually divided to give me that? What actually divided to give me that strange behavior? So we've got to scroll down and find the thing. Let's find the function again, because that's the easiest thing. I should really write down the address, like on a bit of paper. That would make the most sense. But anyway, we're going to do it this way. We're going to run to here. And we can see these mysterious values. Now, if I put it here, for example, right? And I reset. I run. FF08. Maybe I need to, because these are sensible. Div U instead of div. Interesting. But what am I dividing? So T9 and T8 here. So what's T9? T9 is this, which again should be fine. T8 is the size of the table. Oh, but of course, yeah, that makes sense, because this is a very negative number. So I do want a div U. You're correct. Both of these should be div U, because it's a random number. Table under the div instruction. For sign, yeah, I have actually seen that. I have actually, now that I think about it for more than a second, I know exactly what happened there. Cool, so let's run it and see what happens. And it looks like we have no TLB misses, which is good news. Let's up the number. Should I try? Let's try 1,000. This is going to slow down the startup a little. This might break a number of things, but this should only run once, so that should be okay. One slow frame should be fine. Let's try swapping 1,000 things. It shouldn't take that long. It's assembly, right? It runs pretty quick. And let's see if we get a random thing, and let's do a different chest. Oh no, hold on. There's no chests here. I've got these 3 save points, and they're all kind of bad for different reasons. Let's do one where I don't have to fight something. Okay, this is another funny chest that's annoying to get, but testing things is hard. What would be good is if I got these, because my first attempt at building these binary patches, they all Uh-oh. But that's not good. Okay, that's a bad sign. My first attempt at these binary patches, you could load a couple of patches that were all... they would all play nice together because of a couple of assumptions I made, and I want to do that again, but for more complicated patches, I'm going to have to basically write a linker, I think, to bring them all in together. That's my plan, which is a bit silly, but we'll see. We'll see. How does this room go? Is this does every room transition cause this issue? Or is that just an issue there? We've killed room transitions. Okay, that's good. What if I set this back to 10? I didn't actually test this on the last... Did I? No, I didn't. I just amped the number up straight away. With reckless abandon. But yeah, if I write a little linker in Go, I could build these... I could take a .o file and like put them in sequence in memory, and then write some code that called all the functions. I don't know. That would be kind of cool in a way, right? Oh, it worked. It looked like it wasn't going to load. That was a slow black screen. So basically, if I go and open these chests, we expect them to both be dogs, right? That's the way that 10 randomizations works. So will 100 work? Like, why does... I assume that these room transitions feel slow. Have I... I'm not doing this every frame, am I? Like, maybe I've broken the code that actually checks that this is done and to skip it. Alright, let's see if I can despawn a guy. Dogs. Okay, that's cool. Like, at least it works. So, what if I set this to 100? I wonder what we're doing that makes that break, right? Because, you know, intuitively, it'll just mean we're writing to a memory address, we're overrunning the bounds of the table, or doing something silly like that. I'm touching the wrong controller. Dangers of having two controllers plugged in. You tend to touch the wrong one. The really obvious thing is that we're doing this every frame, and that's somehow breaking the transition. And that seems worth pursuing. Because something weird happened there, right? There was like a little skip, and the room load seemed slow before as well. I don't know. That feels like maybe I'm grasping at straws, but... It does feel like there's a little hang there. I don't know. Let's see. Let's go to my execute. Okay, so we load this address. What is this? T0? Oh no, hold on. We load it. T0 is 1. So we jump and we just keep going. Okay, so that's fine. We're not doing extra work. So why does that... What if I divide by a smaller number? What if I divide by like 300? Right? And this lowers the range that we can start with. This makes our random walk stuff a lot less effective. But it also means we're gonna potentially swap fewer things in our table, right? There'll be fewer valid things. Not fewer, but it'll be harder to land on later indices. Impossible, in fact, probably to land on some late indices. It also biases the start, which is probably good because, well, biases the start in a kind of different way, which is good because those are the chests I want to randomize. Those are the ones I want to see randomized here, because they're the ones I'll be able to observe more easily. I just heard a mysterious cluttering in my kitchen, and I suspect there is a mouse sniffing around my I haven't been cooking lots of big bulky meals since I've had the mouse problem, and should I go look? Should I go see if I can scare the mouse off? I don't want it scurrying around. I want minimal scurrying. I want no sniffing, no scratching. Man, I was about to say I'm getting really comfortable with these fights, and then I instantly tank a dumb hit. I think I can despawn him. Oh, don't. Okay, there we go. We're safe. We're safe from more unnecessary combat. This is going to be dogs as well. Of course it is. But they look like different dogs, right? I don't think I'm going crazy. I think those were different dogs. Maybe not. Okay, let's up this bad boy. Let's do it 1,000 times. Let's do it 10,000 times. Let's really shuffle this up. 10,000's a big number. 10,000's probably too big of a number. But let's just do it. I don't know. We'll see what happens. The game's gonna load slower, but I have a speed up, so that's okay. I keep grabbing the wrong controller. It's really, really silly. No. But I did have a guy come today and seal up all the gaps in my cupboard, so hopefully that deters the mouse. Or the mice. Just making sure I can't see one, you know. They're out there. Interestingly, does look like I wonder what that is specifically that caused the room transition to crash consistently. I love that these guys have an attack that just makes them, you know, like you parry them and then like you just kind of harmlessly pass through each other. Okay, here we go. What do we get? Not a dog. It's dogs. It's dogs again. Of course it's dogs. Okay, we've just got to be careful to not spawn more amigos. Okay, I can despawn him. He's gone. He's freaking toast. Yeah. Nice. I'm a pacifist. I'd rather despawn my enemies than... Oh, got to be really careful there as well, because there's just enemy spawns everywhere. And then... Oh, got to open these chests. Got to find out. It's the same dogs. Okay. What I really need is to do my GDB debugging, right? Where I connect with GDB and use that to dump out memory and then analyze what I've actually done. Because that would be useful. Because I should be doing something here, right? And actually, okay, I'm going to put a breakpoint here and I'm going to investigate. I'm going to examine with my eyes. Because that's easier than comparing a bunch of memory dumps. And I'm going to try and do the easy thing. FFOO. Awesome. So I'm just gonna jump here initially. We're gonna find that sequence where it's store, load, store. So this is it. This is where we actually write the stuff. So we want to look at this. Okay. So we're here. We load into T9 from T0. What's T0? So these are both entries in the table, right? This is entry 0. In fact, that's interesting. I wonder if we'll see that always. So we load, we store. That's okay. Aha! I see the problem. Do you see the problem? This register never changes. This register should change. This is always the first index of the table. So how does that happen? What do we put into T? Wait, T1? No, wait, T1 shouldn't change. Sorry, it's T3 and T0. So T3 does in fact change. That looks great. That looks phenomenal. Interestingly, these are the same. So that's... I hadn't thought about them being the same. I guess if they're the same, that's okay. You don't really want that to happen lots, but it could happen. And that's allowed. 3, 1, 5, 7... So that's good, right? That looks great. That looks exactly like what I want. 3, 5, 1, 7, E, C. Yeah, these are swapping. They're swapping around. Where's 3, 5, 1, 5, 3, 0? So this is like the start of the table, right? Somewhere up here. And then these are the... They're down here somewhere. So do these ever swap? Do you ever see things down here swap? Is there a lower floor of numbers that never get reached? Hold on. There's a problem, potentially, with my simulation algorithm, okay? If counts I, if for any valid bit, the number of counts is 0, if we just have not hit it, we want to return the biggest number we can, right? Because that means that something has gone very wrong. Okay, if we haven't counted any numbers, that's a really big problem. So let's try this again. Just to make sure that we can't rule out 131 by way of it having this weird skip property. Because it's such a small table, we could really see certain indices being hard or maybe even impossible to visit. Or maybe just very unlikely. I don't know. Like, my metric I think is good, but maybe... 131. It's just weird, right? It's weird that I wasn't seeing... I'm going to try 18. I'm just going to try a different number. It's weird that I wasn't seeing any of those indices at the start, right? Like, is there a reason that I'm never hitting 0? Because the remainder should occasionally be 0. I guess because it's 470... But you wouldn't think that the little... Like, because the whole register is not a multiple of 470, and we're generating a random... But there's so many multiples of 479 in 3.2 billion that it shouldn't matter, right? It shouldn't matter that it's not, like, powers of 2 or something. That... We should be able to take the remainder. That should work. Let's try this. We're going to do this again. We're going to run it. And we're going to see. I probably have to head off soonish, get to bed. I've got a really big day tomorrow. I've got, I'm going out teaching at like 10:20, and then I've got a singing lesson, and then I'm teaching again. And I'm not going to get home until about after 7 p.m. So it's going to be a pretty killer day. But it's going to be a lot of fun. I'm going to be teaching like Year 7 English, which is going to be great. Haven't done that before. Year 7 maths as well, but a bit of English too, apparently. Okay, so we're going to go here. We're going to go to 315. I've already forgotten. 35153. It's on the screen in front of me, and I've already forgotten. So, okay, so a couple of things are swapping here. I see them swapping, but I want to see something swap like up here. I want to see one of these lines swap. Okay, no, oh, they're going, they're happening. It's swapping. It is happening. It looks like this algorithm works, so that's kind of good. Do we have anything that is invalid becoming valid? Maybe. Yeah, so maybe some of these are still duds. Some of these rights look like they're maybe not correct. But I think the odds of any given thing swapping is still quite low, right? I think that kind of makes sense. It's a little bit of weird bias. But that's kind of good. So it would be interesting to run this and start a new game and just like play through it for, I don't know, an hour or two and just observe with my eyeballs. It'd be kind of hard if all the early chests were biased towards dogs, but you could do that. That would be nice. Okay. Okay, I'm pretty convinced. Let's try it again, right? Because that was a different number, right? We did it with 131 last time. We've done it with 18 this time. That's kind of like trying a different seed. All right, let's see what happens. Let's find out. Oh man. I'm just gonna run around this world and try chests and just see if any of them are not dogs. And that will confirm, like, visually the algorithm's working. There's still a bug with it, and it's really, really hard to write a test for a bug like this, I guess. I could probably write a harness, right? That verified it? It's just where I would run it, right? Do I use QEMU or something and have some kind of weird setup where I visualize swapping and try and make sure all of the indices are valid, or I don't know. Okay, well that's not a dog, so that's good. That is literally what I want to see. Nice. Okay, I mean, I'm pretty happy. I'm pretty happy with that. Maybe 131 was just a worse number, and maybe there's going to be some trial and error to work out what's really ideal here. Let's see. If this chest is not dogs, I'm going to go to bed a happy man. Nice. They're freaking boring items, but that was good. I'm gonna press on. I'm gonna press on. I'm gonna try a couple of other chests. The other fun thing is I need to rig up chests to give random entries from the reward table, and then randomize the reward table as well. That's next. That's kind of the next thing. Oh my god, there's so many enemies in this section of this world. I always forget how overwhelming it is. Oh my gosh. Okay, this is what happens when you try and just like do it quickly because you're impatient. I'm gonna open a couple of chests. I'm gonna open a couple more chests. But I can't really avoid spawning a million dudes. God, the ground combo finisher just really locks you in place for a long time. It's very stressful. And then sometimes the auto attack just hits completely the wrong person. Okay, there we go, there we go. I'm really bad at the spacing for the air hits. There's a real like magic art to it. People that are good at it look like absolute wizards. Okay, there we go, there we go. There's a chest here, I'm pretty sure. No? Would I do all that for an invisible chest? An imaginary chest? It's up here, right? Where's the chest? There's definitely a chest somewhere here. No? Have I already opened them? I've already been through here. Oh, so for some reason on this save file that I made for testing the randomizer, I opened some of the easiest chests to get in the entire game. I need to make a new save file. This is really, really silly. I got the ones... I got them all. Why did I do this? What was I doing when I did this? Did I get the one in the red room? There's a chest in the red room as well, I'm pretty sure. Why did I do this? What was I doing? No, okay, this one's here, this one's here. This is just the most annoying room in the game. It's okay. Oh my gosh, if I die to this... there we go. Okay, okay. It's happening. I need to make a new save file. This is really, really stupid. I need to make one where I just pick up nothing. That's really boring. Okay, well, look. They weren't dogs, and that's good. And we could kind of visualize it actually happening in real time, which was really, really cool. I think I'm going to leave it there. Today, we swapped random elements, and it's taking a really long time to do this basic stuff. We found as close to the optimal value as I could calculate, as far as I'm concerned, for how to walk this table in a relatively efficient way. That was fun. Actually wrote like a full-on simulation for that, so that made me happy. And yeah, we're swapping indices. So this idea of populating the loot table with completely new stuff and then swapping all those around, that's working really well. And I'm going to add some more pre-steps here I'm gonna make this loop a little bit smarter, maybe have a couple of different categories that it picks from, maybe split this into, 2 or 3 smaller loops so that it picks from a couple of buckets, right? So you get 10 high-level equipment items that get scattered through the game, and then maybe 5 of like a different bucket, and then so many recovery items. Just like do it a little bit smarter. That would be good as well. There's also a few progression items that don't get populated in the table right now, such as the thing you need to progress in Halloween Town, and also the Navi Gummies. So there's a couple of special case things to put in here, but I feel like it's coming together, and this is a much better way to distribute and play a randomizer seed. So what did we actually do? Let me check up on my checklist. Fix weird dogs. We fixed the weird dogs. No more weird dogs. We shuffled chests. That's done. Check. We never need to think about it again. Better RNG seeds. So that's probably the next thing to do. I don't know if I'm going to keep doing this on stream. It's a bit weird and esoteric, and I would rather do more Rust stuff. I'm keen to get back to Rust. I have basically this morning finished this gigantic refactor that was really dull and I didn't think was worth streaming. But now that I'm going to do new feature stuff again, I'm probably going to do the left sub-expression recursion elimination. I worked that out. I read a really good article on it. Someone very helpful pointed me in that direction. And I want to do operator precedence as well. So I can probably start to tackle both of those things, maybe in my next stream, which may be tomorrow morning if I'm up early enough. So let's find someone fun to throw a couple of viewers onto with a raid, because it's good to share the love. Thank you everyone who's been with me on this strange assembly journey. Thank you Zymus for your help, especially with the miscellaneous PlayStation 2 knowledge. You are very, very, your knowledge is always very, very welcome and appreciated here. Indie game dev stream in Godot. Liquid Sky, ASMR programming. I love a good Godot stream, honestly. I love a good Godot stream. Ooh. Godot learning. All right, let's throw some viewers over to this person. Making games they want to play. Zymus, thank you very much. Thank you very much. And I hope to continue seeing you around. Let's check out this mysterious looking Godot game. And yeah, thank you everyone for tuning in. It's been really great. I'm enjoying building stuff on stream as always. Let's go over and show this person some love. I will catch you next time. Bye.